Let me go ahead and pray to start with. Again, so thankful you were all here. I really honestly just appreciate your trust in me, that you trust me to be here and teach you about things. So I just want to thank you for that. Let's lift this up to the Lord. Lord, thank you for bringing us all here today. And your word says that heavens declare your glory, and I pray that we can see that today. Maybe in more detail than humans have ever been able to see before. And I really thank you that we live in a time that we can see the intricacies of your plan from the very beginning. Please give us hearts that are receptive to the truth. Help us not necessarily want to be right, but help us want to know what is really actually the case, what is really true. We hear your Son is the way, the truth, and the life, and we know that the truth is inherent in who you are. So help us to see that, help us to change if we need to, challenge our thoughts, and we are so thankful that you brought us here. I pray this in your name. Amen. Amen. So as a quick review, last week, again, I apologize I didn't post last week because it was kind of cut in the middle. We're going to try to put them together and make something that makes more sense. But we talked last week about how we are definitely sure the Big Bang happened. We talked about the cosmic microwave background radiation. And that picture we saw with all the satellites, and then picture of the early universe when light was first able to be released, which is so cool that we can see that. We know this definitely happened, and that the Big Bang causes a lot of problems. I say problems, we were discussing those earlier, where we see this just like this very precisely tuned universe from the beginning. We talked about that analogy of this is a bowling ball. We roll really slowly right down the middle of the alley for a light year. Okay? 1 part in 10 to the 60 off and you're in the gutter somewhere. And if it's in the gutter, then the universe no longer is existing, really. It's collapsed or expanded. We don't have anything necessary for life. So we talked about all those kinds of things. We talked about how the universe is really smooth. Like, matter seems to be really evenly distributed. We don't have these giant clumps that would have collapsed into black holes. We have these really small pockets of organized matter we call galaxies. And all that stuff was set up in the initial moments of the Big Bang. And so we see this, and the Big Bang is incredibly strong evidence for a creator. That we see at the beginning of time. Remember, we also talked about that in the first week, where there's really 2 possibilities, that the universe is infinite, it's never had a beginning, at which point it never needs a creator. Which is the same reason why we don't need to explain where God where God came from, because we say that God has always been here. God doesn't need a creator because he's infinite. And if the universe is the same way, we don't need to explain the universe. But if the universe had a beginning, then that means something had to cause it to be here. Which implies something that is outside the universe, something that is not a part of our universe, something outside acting in on it, which is incredibly strong evidence for the creator. So we see that. We know that something like the Big Bang happened. Our picture might not be perfect, but it's really good. And so we're going to talk a little bit more today about some other evidence that we see in cosmology stuff beyond the Big Bang, but also after it. And we see that the universe wasn't just set up perfectly at the very beginning, but that the universe actually, in the way that it's constructed, is perfectly designed to be, for life to be possible. Okay, and so some of you may have heard some of these things before, but this is a cool quote here. So there is, for me, powerful evidence that there's something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. Okay, and the idea is that we're looking at all these little constants, all these little forces in nature, things like gravity, the power of magnetism, the forces that hold atoms together, things like that. All of those are so precise, it's insane. And we're going to talk about those today. They're off by just a little bit. Things like atoms couldn't exist. Right? It seems like this universe has been lined up just perfectly, not only to exist at all, but also to make life possible. And if we, as Christians, we think that God's purpose in creating was to create beings like us. That was his goal. We talked about the 6-day creation in the first week, and how that's probably best read as literary poetry. But we do see in the culmination of this, on the 6th day, he says it's good, it's good, it's good. And he gets to when he creates man, and he says, it was very good. right? It seems that creating humans was his ultimate goal. And what we're going to see here in even these basic fundamental forces that underpin everything that exists, if those were off by a hair's breadth, the universe collapses and we certainly don't get humans. Okay? So I'm going to give you some examples here. The strong nuclear force, and that's a fancy term, but you're familiar with like the diagram of atoms you saw in high school. Do you remember those? Mm-hmm. Okay, so you got this little cluster of particles called the nucleus. It's composed, and we'll see a diagram of it later, but see a cluster, it's got neutrons, which are electrically neutral, and protons, which are positive. You guys know about magnets and two positive things. What happens with those? Repel. Yes?
They repel.
They repel each other. But the nucleus, that's not the case, right? They're held together extremely strongly, even though they're both positively charged. The thing that holds those protons together, despite their same electric charge, is called the strong nuclear force. It's super powerful. It's way, way more powerful than any of the other forces that we see in nature. It's why nuclear bombs are so powerful. You're releasing that energy that holds those together in a nuclear bomb. So what we're going to see is if that's 1% different, most of the atoms that we have could not form. 1%. 1 part in 100. Okay? Remember, just a quick review on scientific notation. You're going to see a bunch of these today. Remember, 1 part in 100, if I have 100, that's the same as 10 to the second power. There's 2 zeros, you can count them up. Okay? So this is the smallest one we're going to look at today. Okay? This is a fun one. Slight difference in matter over antimatter. That's a fun one. We'll talk about that in a second. But the fact that we have anything at all is sort of weird. And I'll just put it that way. There's also the balance between gravity and electromagnetism. Okay, electromagnetism is the regular magnetism we talked about, where negative and positives attract, and same charges repel. And so those are actually really balanced as well to allow different elements to exist. So that's another fun one. And then the expansion rate of the universe as well. Okay, and these get progressively more unlikely, but there's a whole list of these things, and I'll show you more examples. Okay, so this is an interesting quote here. Similarly, our universe seems fine-tuned to be favorable to life, with its Goldilocks expansion rate, not too fast or too slow, electron that's not too big, a proton that is the exact opposite charge, the same mass as the neutron, not quite true, but really close. In a 4-dimensional space which we can live, the electron or proton were, for example, 1% larger beings could not be. What are the chances all those properties would align to create a nice piece of real estate for biology to form and evolve? The answers are really, really low. That's good. Okay? So here's a fun picture of an atom for you. Again, these diagrams are actually kind of bad, but that's because atoms, when we look at them, they're so complicated it's actually hard to draw good diagrams of them. And the picture of the nucleus is way, 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 way too big.
I know how small is the nucleus.
What's that?
The nucleus would be a marble in a football field.
That's actually pretty accurate. Yeah. If your atom's a football field wide, one marble would be about the size of the nucleus. So we can't actually draw very good diagrams of atoms. They're really complicated. Electrons don't go in a perfect sphere like this. They go in these weird shells and stuff like that. This is a picture of the oxygen atom, at least a diagram of it. Again, we can see the strong nuclear force. These red ones are protons. They're all positively charged. This is the carbon atom. You can see that they're positively charged and they should repel each other, but the strong nuclear force is an additional force that holds those together. The electrons are bound to the atom by the standard force of electromagnetism. They're oppositely charged. They want to go around and be close to those protons. Okay. Now, again, if this is 1% different, the force that holds the protons together. Okay, if it's 1% different, a whole bunch of bad things happen. All right, tons and tons of bad things happen. We think that most of the things that make up the Earth came out of stars. Right? Stars get really big at the end of their lives, and sometimes they explode. The explosion creates all of the heavier elements, most of the things that we are made of. Things like carbon and oxygen and all the important elements for life came out of giant stars exploding billions of years ago. Now, if you have a strong nuclear force, 1% larger, the fusion that is basically the power that's going on in stars has a lot more trouble happening. Stars actually don't ever get to the point where they're able to get super large and explode. Fusion doesn't really happen particularly well. You have all these sorts of problems. Bigger atoms can't even really form. You've got too much power going on holding those things together, and it ends up totally messing up the way that atoms form at all. If it's a little bit weaker, you have lots of other problems that come out of it. The stars would have gotten way too big, would have fused way too fast. The universe actually would have burned through most of its fuel already. We wouldn't have anything at all right now. And that's just a 1% difference. It's really a problem. There's other problems with this as well. I don't want to get super technical, but mostly just to suffice it to say, if you change that strong nuclear force by 1%, basically all chemistry doesn't happen. Certainly not the chemistry that's complicated enough. You've seen the periodic table of elements.
Mm-hmm.
Yeah, there's a lot of different things on there. Most of those couldn't be around at all, just by 1% difference. And so it's a big problem. Like, well, why is that? Because again, if you're coming with the assumption that all of this is an accident, that means that this just happened to be just perfect by chance. And that's sort of a problem, right? If you're looking at a really precise thing, it just happens to be there, and your only explanation is chance, 1% is actually not very good. Okay? It's really not very good. So this is a fun question. But why is there anything? So we talked about this in a more general sense last week with the Big Bang, and like, okay, so there is a universe, right? And we see that it had a beginning. But the problem is, we talked about this at the very early part of the universe. Like, it was just so hot and dense and crazy in there that all matter had broken down. Like, you don't have atoms then. All of the forces that make our universe, they like boiled together in one weird, strange soup, and we don't even really know what it's like. But we know that there's no way that matter is really a thing. It's just this. You can imagine, when you boil something, it sort of melts. Like, it sort of decomposes. It's not hard anymore. Like, you can melt steel, and like everything eventually melts. Now imagine the entire universe getting so hot it just kind of melts. All of the forces kind of melt together. You don't really have anything other than energy. All right, as it cools down, we have this really fun equation here that we've heard before. Well, we'll get to that in a second. Let's see, where did I put it? I know it's in here. There we go. So, you've heard of this equation, E equals mc squared. It's Einstein's famous equation, we all know it. What that really means is that, so do you guys know what the different parts actually mean?
Energy, mass, light, speed of light.
Nice, excellent. So E is energy, M stands for mass, and C is actually the speed of light. It's a big number. And we're going to multiply it by itself. Okay. So what Einstein, in this equation is discovering that when you turn, so this is mass, you can think of it as matter, stuff. When I turn stuff into pure energy, you're turning whatever stuff is, you're multiplying it by the speed of light. You get a ton of energy coming out of any sort of matter, no matter how small it is. Okay? But it also means you can actually turn energy into matter. We can actually do a little bit of math here and see what it would look like. I tell my students when you're solving for a variable, you do the opposite. This is multiply it, so you're actually going to divide to do the opposite. We have to do the same thing on both sides, don't we? You know that?
Yeah.
Okay? Anybody know what something divided by itself is? One, cool. So that's just mass times 1. I'll just do a little 1 there. Okay, so you can actually create mass out of energy. Which is cool. It takes a lot of energy though, right? Taking however much energy dividing by the speed of light squared, you actually get matter out of this. We do this in, if you've heard of the Large Hadron Collider, We actually see this occur. We have tons of energy going into very small space. We actually see particles form. I tell you this because we see this soup at the beginning of the universe, right? This tons of energy like boiled together. Eventually it cools down enough and you see matter start to form. But some weird things happen when you create matter out of energy. Everything in this universe is very balanced. Thanos would like it. 4 of you knew that was funny. Okay, so that's all right. I think I actually put that equation.
You should get paid for
I already put that in there. So
that's why they call it balance of nature.
correct. Yeah.
Which
So
it should change.
exactly. So I mean, Thanos had the right idea. No, he didn't. Please don't assume that. So anyway, when you create matter out of pure energies, weird stuff happens. So we talked about the atom, and it's a positively charged proton, negatively charged electron. Okay, we call that matter. There's actually an opposite of this. It's called antimatter, which is really weird. Okay, now this is actually, it's used in Star Trek, but it's a real thing. And antimatter has a negatively charged proton called an antiproton, and has a positively charged electron called a positron. It's an exactly mirror image opposite of matter. And some cool things happen when you have matter and antimatter meet. Okay? They're opposites, and they annihilate each other. That's the word annihilation is for. Okay? They turn 100% of matter into pure energy, which is why they use it in Star Trek as a hypothetical power source, because it's the most possible power you could ever get out of anything. You're turning pure matter into pure energy. And we talked about how much energy that is, right? Equals mc squared, timesing by the speed of light. It's an enormous amount of energy. You know, a teaspoon of antimatter would destroy most of the United States in one explosion. It's insane. Like, this stuff is very, very powerful. So now, keep in mind though, when you're creating matter out of energy, it comes out perfectly balanced. It should create, and this is what we always see in our particle accelerators and everything, when we do this in labs, we always see one particle of matter and one particle of antimatter created at the same time. It's balanced. Okay? You don't just get all matter or all antimatter, you always get an exactly equal amount of both. So what would happen in the early universe if suddenly all this energy turns into matter? What should have happened? You should have had half of it be matter, half of it be antimatter, and then what would have happened? It's all close together in this boiling soup of energy. It would have annihilated each other, and we shouldn't actually have anything. Like, there should be nothing here. Does that make sense?
Yeah.
But there is.
Yeah.
There is stuff here. It didn't all annihilate, and for some reason, and again, we have no evidence of this anywhere in the lab ever. Every time we've done this in the lab, no matter how many particles we create, it's always a perfectly balanced one particle of matter, one particle of antimatter, because they're always canceled, created in equal parts. But the question is, why is there anything and nothing? We should just have this weird soup of light and nobody around to see it. Okay? Turns out, there was one extra particle of matter in a billion than antimatter. 999,999,999 particles annihilate each other, and there's one left over that was matter, and that's what everything is. That's, yeah, right?
That's what matters.
So how do we
Okay.
know? How do we know?
One part in a billion. Okay? Yeah.
So how do we know that? Because you said this.
That's a great question.
The studies we've done, it's always been equal.
Exactly. Well, clearly there is something. So there had to be an imbalance at some point. We know it's about this number. I mean, some of these numbers are not perfectly precise. They're still being studied. They've only been discovered in the last 10 to 20 years, a lot of these things. So this number might adjust by a factor of 10 or something, but we're talking about just like a very small outnumbering of matter. And we can see that in things like the cosmic microwave background radiation. We see all this light, all this energy. The explosion was big enough, we can still measure the heat today, almost 14 billion years later. Right? That heat is everywhere in the universe. Even where there isn't matter, that heat is still there. Like between galaxies, we measure the same temperature. which is crazy. So we actually, like, you can figure out about how many particles there have to have been with something like that. Again, it's an estimate, but you know that it's a very slight amount over that was matter, and we don't know why. Okay. Again, that's sort of a problem because if it should have been balanced, everything we see should have been balanced, but it's almost like something wanted there to be something here. Okay. There's balance of gravity and electromagnetism. Okay, so these forces balance each other out, and they also help stabilize things like the atom. Gravity is a lot weaker than magnetism, which is why when you have a magnet, clicking together doesn't like fall off. Gravity doesn't pull it down. Right? So magnetism is a lot stronger, and it needs to be a lot stronger, but it's also really precisely balanced to help things stay together in the atom. Okay, and again, we have some of the same problems with stars forming and everything else. And this is specifically the ratio of those two forces working together, creating the chemistry and fusion in stars and things like that. Okay, this is a little bit more balanced, or a little bit finer tuned. It's not 1% off like the strong nuclear force. This can't deviate by more than 1 part in 10 to the 40. Christy, your eyes are very large right now, and that is exactly the right response. Okay? That's a big number. Okay? Now, we've talked about big numbers before. Remember, that's 10 with 40 zeros. And our brains have trouble understanding big numbers. Our brains have a lot of trouble understanding big numbers. So I did some math on this, and I wanted to see if we can illustrate just how large this number is. Okay? And by large, I mean small, because what you need to imagine, okay, you need to imagine a ruler with this many little slashes on it. And I've got the dial, okay, you got a bunch of slashes, right? And my dial's right here, okay, and it can't move one over here, and it can't move there. It's got to be exactly there. The universe doesn't really work. Okay, and again, some of these numbers, you'll get different numbers for this, depending on the scientist that does the measurements. I've seen as low as 10 to the 34, as high as 10 to the 42. I actually chose 10 to the 40 because of the illustration I can show you. That's really fun. Not because there's any great reason for it, but I've seen all these numbers in between. Again, these are new discoveries, so we don't have them like really pinned down yet. There's research being done on it all the time. The specific number actually isn't important for the argument, because no matter what you're measuring, it's really, really, really precise. Okay, so let's see how big that ruler would have to be, how small those slashes need to be. So we're going to talk about how exactly small is that. So I've got a picture of E. coli here. You guys know what this is? What E. coli is? What is it?
The bacteria that produces vitamin K.
That's good. It's in your tummy. Okay, it helps you digest stuff. Okay, it's a really important one. When it mutates, sometimes it makes you sick. But this is a bacteria. So lots of them. There's actually more bacterial cells in your body than you have human cells. It's crazy. There's bacteria everywhere. You wipe this, put it on a petri dish, and there's going to be millions of bacteria there. They are everywhere, in everything, all over the planet. Every place we look, we can find these things. Now, 10 to the 40th is a really good number for bacteria because we think, ballpark estimate, that's about how many bacteria have lived on Earth in its whole history. So you count every bacteria that's ever lived and ever died, and it's about 10 to the 40. Again, maybe we're off by a factor of 10 or something, but this is a big number. So here's how many E. coli is that? Like if we wanted to actually, if we really wanted to know this, how far is, how big is 10 to the 40? So you wanted to line all these bacteria up, 10 to the 40 bacteria, end to end. How long would that be? Any guesses? This is going to be fun.
Would it be as long as you could circle the sun?
Great thought. Okay, so we could go around the sun, maybe like the orbit of the Earth, or are you thinking like close to the sun?
Really close.
Okay, so like an orbit of the sun. Not just an orbit around the planet, an orbit around the sun. That's a great guess. Any other guesses?
The length of the galaxy.
You think it's the length of the galaxy. Okay, what else?
That was going to be my guess.
You guys are kind of annoying me, actually. If you were to line all those bacteria up, end to end, it would stretch from one side of the Milky Way galaxy to the other. That's 100,000 light years.
How long is that bacteria?
Whoa.
Huh?
How long is the bacteria?
It's nanometers long, very, very small. Okay, and they're actually very consistently sized, which helps. Yeah. So and so that's your ruler. Okay, that's your ruler. It's 100,000 light years long, and it cannot move by more than the width of one bacteria, or the universe does not exist.
I gotta wash my hands.
Okay. Okay. I mean, we're talking precise. We're talking absolutely precise. Okay. The expansion rate of the universe. Again, we talked about some slightly different problems. Yeah.
So, I want to rephrase what you're talking about here. It's not just that this is super unlikely,
Correct.
Super precise. It's that it's super precise, and you see purpose behind it.
Well said. That's exactly right. Because again, and the purpose that we see is, and we're going to refresh this later, but I appreciate you bringing that up. Because low probability things happen all the time. The point is there low probability with a purpose? Right? And the purpose that we see is that all of these things are necessary for life to exist. Okay? Life does not happen if these are not balanced on a razor's edge. Okay, in some cases, the universe just completely disappears, like the case of antimatter and matter. There isn't even any stuff. Right? Yeah.
But you're not saying life only exists here, so the question of is there life elsewhere?
We'll talk about that later too. That's a fun question.
Okay.
It's called the Fermi paradox. So that's really fun. We'll talk about it. Okay?
Another, I
yeah.
don't know if it's a question or a comment, but we'll see if I put a question mark at the end.
Okay.
Low probability doesn't mean impossible,
Correct.
but how big does the universe have to be for something like this to happen, even if you don't have purpose?
That's the question, right? And it's not. And this is the problem with this is an innate property of the universe, no matter where you look. And as far as we know, there's one universe. So you have one shot at this. So this isn't just a property of our Earth. This is the whole universe together, the balance of electromagnetism and gravity. And I'm just using our galaxy as an example of how precise it needs to be. But that's true for everything, everybody. No other galaxies would exist either if this is off. So we have one shot at this. Okay? Yeah, Kirsty's starting to sing M&M 2000. Thank you. So expansion rate of the universe, again, this is something we have talked about a little bit. But again, think of the initial explosion of the Big Bang throwing stuff apart, right? So that speed has to be actually pretty precise. Because if it's too powerful, you don't get stuff clumping together in galaxies and stars. If it's not far enough, then gravity pulls it back together and you don't actually get a universe. This is balanced in 1 part in 10 to the 60. We just talked about how big 10 to the 40 was. It starts at that point, you start getting so large that it's just, like, I can't even come up with good examples of something to relate it to. It doesn't make any sense. Okay? And again, this is another case where the universe simply does not exist. Because it's already collapsed together, or all the galaxies were flung apart too quickly to clump together. Like this is, it's so precise, it's on a razor's edge, it doesn't make any sense at all. Here's some other examples of fine tuning again. These aren't all of them either, but I just threw a couple of them that I thought were sort of interesting. Fusion efficiency of hydrogen, gravitational constant. Again, some of these numbers are a little different depending on where you grab them from, so you heard me talk about gravitational constant. So electromagnetic force versus gravity. This one said 1 part 10 to the 37, again. So that's, we said 10 to the 40, I've seen as high as 10 to the 42. Again, those numbers just sort of vary a little bit. Yeah.
So when you use the word fusion, you're talking about what they understood to create the hydrogen bomb.
Correct. And fusion is what occurs in stars. So Fission is how are we seeing the strong nuclear force.
Mm-hmm.
Fusion is when you shove stuff really close together and actually new atoms merge together. You can basically force protons to stick together. They don't want to until they get really, really close and really, really hot. And what happens there is they actually release a little bit of energy. So fusion actually is a tiny amount of antimatter and matter annihilating. That's actually where you get the energy from. So it's actually more powerful than fission, which is breaking apart the strong nuclear force. That's where that energy comes from. Fusion, you actually fuse stuff together and then stuff changes and actually you get a little bit of antimatter created that annihilates.
So that's why a hydrogen bomb is infinite, or not infinitely, but much more powerful than an atom bomb.
Yeah, depending on the efficiency of your atom bomb, you get about 4% of the matter turned directly into energy. In a fusion bomb. Okay, that's what you probably heard of as an H bomb right now. That's the same thing because it's fusing hydrogen together, which is right here. Actually, isotopes of hydrogen, but that doesn't matter. Okay, cosmological constant is another fun one. 1 in 10 to the 120 power. That is that number just. There's 10 to the 80 subatomic particles in the whole universe. This is 120. Like, I don't even know how they get that number, to be honest with you. But I do know that that's essentially the force that's expanding the universe today. And if that's off a little bit, again, it's even more precise in the expansion rate of the universe. Mass density of the universe, again, that's the same problem we had earlier. Expansion rate of the universe. Initial entropy, I threw this up there, so it's kind of funny. So 1 part in 10 to the 120. This number has more zeros than the subatomic particles in the universe by a lot. That number I don't think is a great example, honestly. It was thrown offhand by a guy named Dyson of Dyson sphere fame. If you've ever heard of that, it's a science fiction concept. And he basically, entropy is a measure of disorder in a system. So if your room's really messy, there's lots of entropy in your room. Okay? Stuff that's really organized has low entropy. And he's like, the universe was super organized when it was started. That's how we see all this precision happening. And he's like, yeah, I don't know. If it was off by a little bit, because again, when it was really small, it had to be so incredibly organized, so when it's spread out, we still see what we have today. He's like, I think the initial entropy, and it was kind of an offhand comment. There's no actual data that goes with that one. But he just threw it out there, and I think it's kind of sort of a fun one. So, again, we looked at some stuff. But 1% is not that bad. Okay? Like the things of, the strong nuclear force. But the question that and you were asking this earlier, how bad does the odd need to be before we can start thinking about design? How bad do the odds have to be before you can start reliably concluding, okay, somebody intended this to happen? Okay? For example, if somebody wins the Powerball, it's a really low likelihood. It's about 1 in 300 million. Is that design that they won that?
No.
No, because there was a lot of tickets sold, right? But what if they won it twice in a row? What if they won it 5 times in a row? Would you start being like, wait a minute. Somebody's rigging this system, right? You can start to conclude this, and we start to intuitively understand something going on here. And again, it's not just a low probability, but the fact that the low probability gives us life in a universe at all. Okay? And so we just see that the universe is sort of balanced on this razor's edge. Like the tiniest deviation, the universe just stops being anything close to what we see today, certainly not capable of supporting life of any kind. Okay? And there's really 3 possibilities to explain this. One, that it happened by natural law. Basically, there's some sort of rule that says the universe had to be this way. Okay? In the same way that I can drop a pen and it has to fall because we've got force of gravity. Maybe there's some bigger force at work that kind of constrains the universe, that all these things have to be this way. It also could happen by chance, could have been an accident. Again, low probability things happen, like people win the Powerball. Okay? You could flip a coin a bunch of times, and that ordering of heads and tails is incredibly low probability. Those things do happen, or it could have happened by design. Somebody intended it to be there. And the thing is, I think we can rule out the first one pretty easily, and very few people actually think of this as a possibility. Because if you have a natural law, you're already talking about something outside of this universe anyway that's somehow constraining. So that's some sort of rule outside already. That actually blends very smoothly into design. Because who made that law? Who designed that law? Why is there a law at all that is outside the universe? Things like that. And chance, again, is a possibility. But the trick is there a purpose to this? Okay? I showed you some of these pictures before that I took on a hike of a 14er, and you see these little things on the side of the road, or on the side of the path. These little weirdly stacked rocks that are just like, man, that's really unusual. That's a low probability arrangement of rocks. But they seem to be balanced, which implies a purpose. It's not just low probability, but they seem to be placed just so that they are balanced and they will stand up. And the question is, when you see these kinds of things, you're like, huh. And you start to see, and we reliably conclude that somebody made those because they're balanced. Because they seem to be an indicator. We call them cairns, and they mark the trail when you just have nothing but rocks. So like, okay, how do I determine this rock is the path and that rock is not the path? People put these little cairns on the side of the trail so you know where to go. And then you get to the top and people are like, let's see how high I can get this. All right? And you stack that to the moon, we start talking about the balance we see in the universe. Actually, it's not even close. You need to be like, through the solar system to Pluto. So again, the probability bad probability doesn't mean that God did it. But when we see low probability and purpose behind it, the ability for life to exist, the ability for the universe to exist, balance, then we can start concluding design because we see that there's a reason behind it. It's not an accident. Accidents tend to be random and disorganized. Okay, a weird pile of rocks. But purpose and balance, you see that someone had to do it. Okay? So here's just a quick comparison. Okay? So idea that something created this, something designed our universe. It had a beginning. That's the strong evidence that something created it. Okay? We see perfectly balanced since the moment time began. We see that definitely. Okay, we talked about that last week. We see an incredibly fine-tuned universe. We also see that. Okay, and it's not just fine-tuned, but it's fine-tuned for a purpose. It seems to be that without this particular fine-tuning, you don't have the existence of life. All of these things seem to imply a designer or a creator. Now, again, we can sort of rule out the idea of natural law. Nobody really considers that as a good chance. So the question is, what would you need to have this be chance? Okay, the universe would need to be eternal. Okay, then you wouldn't need chance as much because you wouldn't need to explain all these things. This wasn't a beginning. We see that that's not true. Okay, since it's not true, the odds are so bad that you actually need more than one try. The reason we know that Powerball winners probably aren't rigging the system is because out of 300, 1 in 300 million chance, there was 100 million tickets sold. Okay? And in that, suddenly the odds aren't nearly as bad. It's 1 in 3 that somebody's going to win, rather than 1 in 300 million. Okay? And so the only way to get that is if you've got more than one universe. It's like you were saying, like, wait, how big does the universe need to be? No, how many universes does there need to be? Okay? So, and you saw how bad this is just for the balance of gravity and electromagnetism. And we're stretching bacteria across the galaxy, and there's one off. Okay? So there needs to be a lot of universe, not like 2. It needs to be something approaching infinity of universes. Okay? And so there's this thing about inflation that we're going to talk about in a little bit. And any evidence for multiverse. So I want to show you a video here that I think summarizes this really well. It's just a few minutes long, and I think it's worth showing. Let's see if I can get this to play today. Okay. There we go. And Again, you might see some slight differences in some of these numbers, but that's not
From
important.
galaxies and stars, down to atoms and subatomic particles, the very structure of our universe is determined by these numbers. These are the fundamental constants and quantities of the universe. Scientists have come to the shocking realization that each of these numbers has been carefully dialed to an astonishingly precise value, a value that falls within an exceedingly narrow, life-permitting range. If any one of these numbers were altered by even a hair's breadth, no physical, interactive life of any kind could exist anywhere. There'd be no stars, no life, no planets, no chemistry. Consider gravity, for example. The force of gravity is determined by the gravitational constant. If this constant varied by just 1 in 10 to the 60th parts, none of us would exist. To understand how exceedingly narrow this life-permitting range is, imagine a dial divided into 10 to the 60th increments. To get a handle on how many tiny points on the dial this is, compare it to the number of cells in your body, or the number of seconds that have ticked by since time began. If the gravitational constant had been out of tune by just one of these infinitesimally small increments, the universe would either have expanded and thinned out so rapidly that no stars could form, and life couldn't exist,
This is the expansion rate of the
or
universe
it would
we're
have
talking
collapsed back on itself with the same result: no stars, no planets, and no life. Or consider the expansion rate of the universe. This is driven by the cosmological constant. A change in its value by a mere 1 part in 10 to the 120th parts would cause the universe to expand too rapidly, or too slowly. In either case, the universe would, again, be life-prohibiting. Or, another example of fine-tuning. If the mass and energy of the early universe were not evenly distributed to an incomprehensible precision of 1 part in 10 to the 10 to the 123rd, the universe would be hostile to life of any kind. The fact is, our universe permits physical, interactive life only because these, and many other numbers, have been independently and exquisitely balanced on a razor's edge. Wherever physicists look, they see examples of fine-tuning. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life. If anyone claims not to be surprised by the special features that the universe has, he's hiding his head in the sand. These special features are surprising and unlikely. What is the best explanation for this astounding phenomenon? There are 3 live options. The fine-tuning of the universe is due to either physical necessity, chance, or design. Which of these options is the most plausible? According to this alternative, the universe must be life-permitting. The precise values of these constants and quantities could not be otherwise. But is this plausible? Is a life-prohibiting universe impossible? Far from it. It's not only possible, it's far more likely than a life-permitting universe. The constants and quantities are not determined by the laws of nature. There's no reason or evidence to suggest that fine-tuning is necessary. How about chance? Did we just get really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe inhabited by billions of other observers. So even if the multiverse existed, which is a moot point, it wouldn't do anything to explain the fine-tuning. Given the implausibility of physical necessity or chance, the best explanation for why the universe is fine-tuned for life may very well be it was designed that way. A common-sense interpretation of the facts suggests that a super-intellect monkeyed with physics, and that there are no blind forces worth speaking about in nature. The numbers one calculates from the facts seem to me so overwhelming as to put this conclusion almost beyond question.
This guy came up with a steady state theory.
There is for me powerful evidence that there is something going on behind it all. It seems as though somebody has fine-tuned nature's numbers to make the universe. The impression of design is overwhelming. The heavens declare the glory of God. The skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they reveal knowledge.
What, we can find this
I
thing you
will-
just played on YouTube?
Yeah, and I'll link all these things for you. Anything that I use.
Yeah, I'd like to have that link.
Wait, what's happening?
Silence, come to.
There we go. Something's playing in the background.
What was the title of it?
It's called the Fine-Tune Universe. And again, I would be happy to share links and email. If you're not on my email chain, feel free. I'm going to be posting these every week when I can get to it. So, anyway, so we talked about these already. Again, I always talk about best arguments against this. Because again, I don't want us to do the same thing that I feel like people accuse us of, is never looking at facts. Again, I want to know the truth. I don't necessarily want to be right. So I want to look at the best arguments from the opposite side. So, a guy named Victor Stenger wrote this book called The Fallacy of Fine-Tuning, and this is how he characterizes the argument. If the force of gravity were a few percent weaker, couldn't squeeze the center, or couldn't squeeze the heat, I can't read. It would not squeeze and heat the center of the sun enough to ignite nuclear reactions that generate sunlight necessary for life on Earth. But if it were a few percent stronger, the temperature of the solar core would have been boosted so much that the sun would have burned out in less than 1 billion years. Not enough time for the evolution of complex life like us. Can anybody figure out what's wrong with this? Why is this a bad argument? Again, this is part of his analysis of the argument of fine-tuning. Yeah.
Because it's a bad argument because it's just talking about that it's low probability alone.
Partially, but he also completely misses the data. A few percent.
Yeah, it was just like one.
Remember, this was 1 part in 10 to the 60. That's not a few percent. All right. I mean, not to do too much math for you, but 10 to the 60 is a lot less likely than a few percent. So a lot of ways people get around this is they mischaracterize the argument. They kind of try to wash away just how fine-tuned things are. Like, oh no, it's really not. I mean, it's probably still, it's chance. Yeah, a few percent here and there. I mean, maybe it happened. Not really. Okay, this is one we talked about last time. It's called the weak anthropic principle. Here's a quote sort of explaining it. We should not be surprised or befuddled that the universe is adapted to our needs, since we evolved within the universe and its parameters. Feels really circular to me. Why is the Bible true? Because the Bible said so. Or why is the universe fine-tuned? Well, because we're here to see it. Why are we here to see it? Because the universe is fine-tuned. Why is it fine-tuned? Because we're here to see it. I don't think that's a particularly good logical argument. I feel like it's fallacious in a number of different ways. I don't think it's a particularly good argument. Yeah, Tim? I'm just stretching. Okay. Sometimes you'll see people critique this designer or creator, right? And this is some of the arguments that you'll read about. Like, well, if he designed it, why is the universe so inhospitable in other places? why don't we see more life? Every other planet we see doesn't seem to be able to support life.
So this thing created a universe and people are criticizing it.
Well, okay, the creator was so inefficient. Like, look at this huge universe, and this is pretty much the only place we think life exists.
I bet there's many other places life exists.
There might be. We just can't find them. Okay? Why did the creator take so long? Almost 14 billion years for today? Come on. It's so inefficient. Okay? Why wouldn't the creator want more life than just one planet?
We already don't get along on this planet.
Okay. So can you think of any possible answers to this? You already said one. But anybody else think of another answer to some of these critiques? Yeah.
I was talking to a friend of ours, this is 30 years ago, and
You have a great memory.
Dr. David Cole was he was the head researcher at University of Berkeley.
Okay.
And I asked him once, he's a wonderful Christian.
Okay.
Was, he's now died. And I said, how do you explain God, whom you believe in, and yet you're this profound scientist?
Mm-hmm.
And his answer to me was so simple, but I can't understand it. He said, look at the human eye.
Mm.
You cannot deny God is the creator.
We're actually going to discuss specifically the human eye in a couple of weeks when we delve into biology. And the best counterpoints for it, of course, which are terrible. But anyway, I think like if you see design, but then you create or you criticize the designer, it sort of feels like, so you think you could do better? You might do differently, but like that doesn't get away from the fact that the implication of design is overwhelming. It merely shows the fact that, hey, different people think differently. And maybe you would have designed it differently. I'm really glad you weren't the one who designed it. Okay? In fact, the only consistent critique is the multiverse. Okay? And as the video just suggested, there's a problem with it. Okay? The multiverse has no evidence supporting it. So to even suggest it, to explain the multiverse, you have to appeal to faith. You have to hope. Well, I think there's got to be multiverse. See, because the chances are so low. There had to be more than one chance. I mean, we got to have like an infinite number of universes, or this never would have showed up. But we could also see design, like purpose and balance, and all these things that we see in regular life. Like we already know what design looks like. Yeah, but I think it was chance, and I really want it to be chance.
Because you have to be right.
Exactly, and that's the problem with multiverse. The way that they explain multiverse is this theory called inflation, which includes a multiverse. Okay, and so essentially the way it works is this. We talked about inflation briefly last week, but it's the idea that the initial moment of the Big Bang inflated exponentially. I mean, really, really exponentially. Like every just tiniest part of a second, the universe is doubling in size. So by the time we got 10 to the minus 32 seconds in, that's pretty small, that the universe has doubled like 100 times or something. Okay, if your house appreciated that quickly, you'd eclipse Jeff Bezos. Okay, and net worth. Okay.
It's nice to have our house double in size.
And value either. Doubling in size would be nice as well sometimes. So, but that's essentially the universe, right? And so what that does is it fixes a lot of the initial problems we saw in the Big Bang as we were discussing, right? You have this smoothness, and what you can assume then is that everything was the same, and if it blew up really quick, then little quantum buzzing fluctuations in the atoms and little particles in there basically created the little fluctuations we see that later turn into galaxies. The bowling ball you rolled really slowly down the center of the aisle for a light year. I mean, if you roll that bowling ball at light speed, suddenly it's a lot more likely that you're not going to miss. Okay, it's still a good shock, but it's not nearly so unlikely. And so it's this idea that it's inflating internally really quick. And it's all based on, anyway, we'll talk about that. But anyway, we'll get there. Sorry, I don't. Basically, the idea of the inflation field, or inflation, is that somehow underpinning all reality is this idea of an inflaton field.
Do we have evidence for that?
Of course not. What we do know is that there are other quantum fields. So this is going to sound a little weird because you're like, wait, quantum? That's hard, isn't it? Kind of, but I think we can talk about it in a way that makes sense. So why is it that wherever you have a magnet, anywhere, it always will attract things like metal things?
The electromagnetic force.
The electromagnetic field. Okay, so there's this idea that the force exists everywhere, in all places. Think of like a big ocean or something. Okay, and then you put a magnet, and that makes a ripple in that water, and it makes a wave or something if it's a big rock. Okay, and so when you have fields, the forces that we see are simply ripples in that field. So you can imagine the magnet is like, when I have a magnet somewhere, it's like dropping a big rock into a pond, and you see ripples. And so we see the effects. The field was there. The water was there. The ability for magnetism to happen was there in all places. And it was simply the act of dropping the rock in the pond that made us see the waves that could change things. And so the magnet would simply be the rock. And every force that we see has a corresponding field that goes with it. So the strong nuclear force has a field. So no matter where an atom is, that force that holds protons together still exists. No matter, the electromagnetic field also includes light waves, by the way. Okay, so no matter where light goes, it has a place to live, right? It has a pond with which it can ripple. Okay, and that's the basic idea of quantum fields, in as simple as I can make it. The idea is that there is a field of inflatons. That's the field there. And so that there's this field, and the property of this field, instead of ripples in it creating electromagnetism, is that this field has the property that it increases exponentially, just constantly inflating everywhere. Okay. Our universe then was formed when a patch randomly stops growing through a quantum fluctuation. Okay? We see weird things happen. In fact, in your phones right now, sometimes the electrons just kind of teleport to another place. They actually have to account for that in circuitry, which is crazy. Okay, so we see quantum fluctuations happening. Like, well, there's this field, maybe there's a quantum fluctuation. That happens, we see it. Okay? And maybe that quantum fluctuation, it basically lowered the energy, and then basically it stops inflating exponentially. So then you have this little patch that begins to form like this seed of an ice crystal or something that slowly starts to grow. And that's where the universe comes from. As the inflatons, high energy that started with decays, that's where our matter comes from, and energy. So it's simply all the energy we see is the massive energy of this field that's inflating exponentially. Those decay and create, again, through E equals mc squared. There's lots of energy, so they create all the matter. Okay? The crazy thing is, if it's just a quantum fluctuation creating our universe, that means there's probably other quantum fluctuations creating other universes, and therefore we have an infinite or nearly infinite number of universes. The inflaton field could be infinite and not need an explanation. It's kind of a cool story. Okay? And since it's eternal and it's inflating exponentially, there's always going to be more universes, and eventually ours will happen. Okay? Even with fantastically low odds like winning the lottery, if you have enough chances, it will happen. All right? So, creates multiverse. Nice. What do you think of this? Just initial impressions.
I think these physicists and very intellectual scientists have more blind faith than I do.
Don't underestimate your blind faith. That's my wife, so I'm making fun of her. Yeah, and again, we've never seen an inflaton field. We have no evidence of it. We can't see other universes because, again, we need that third evidence pointing toward this. And so we really have, this is pure mathematical speculation. I mean, it's sort of elegant if you think about it. Like, okay, it sort of relates to something. But when I write I've written a couple of novels. I can create a very consistent universe that has nothing to do with reality either. So, yeah.
Can you help me out for a second and define what you mean when you use the term universe? What is that word?
Yeah.
How are you using that?
It's the best as we understand it. So it's the space where everything that we can see and detect exists.
Okay.
So we usually call it the observable universe, because there's probably more universe that we can't see because light hasn't had enough time to reach us.
Then the follow-up question would be, is the visible, observable universe that we can see, we got the Hubble telescopes and everything, is that infinite?
It is not.
Okay.
What we can see, the observable universe that we can see is 93 billion light years across.
So there's
Yes.
it's a big space in it. It's all
Yep.
contained
Mhm.
in this
Now,
big-
there could be more that we can't see.
Right.
There probably is.
Okay.
But
Thank
we
you.
don't know.
Thank you.
Okay. So the question is this a good thing? And we've never detected an inflaton. We have absolutely no evidence whatsoever to support this. It does create a convenient mechanism for the multiverse to exist without a multiverse generating machine, which sort of sounds hokey, but this essentially becomes that. It's just a quantum field instead.
Maybe the universe created, what if a universe just shot out another universe?
Yeah, they had some babies, right? You don't know. That's essentially what the inflaton field does, is it creates universe babies, okay? There's another possibility that I think is more compelling to me. Again, looking at this, because I want to know the truth, I don't want to be right. To me, I think that the evidence for design is much stronger.
Mm-hmm.
Okay? So, and most scientists agree with this. In a universe that is, in fact, the only universe, the chances are vanishingly small of this fine-tuned space being thing. But in an internally inflating multiverse, it is certain that one of these universes would turn out like ours. Each island universe can have different physical laws and fundamentals. Given infinite mutations, a universe like on which humans can be born will be born. Multiverse actually explains why we're here, and our existence therefore helps explain why the multiverse is plausible. You can see that circular reasoning.
Yes.
Okay. Why are humans here? Because of multiverse. Why is the multiverse here? Well, because we're here. And again, you see that circular reasoning in all of this. And to me, none of that works because you don't have any additional third-party evidence pointing toward it. Nothing else that we can see that provides additional evidence. Okay? Here's another example of it. Even if some of the parameters turn out to be fine-tuned, the author argues this could be explained if ours is just one universe in a multiverse, an infinite number of universes, each with different physical parameters. We would have then ended up in one where the laws of physics are fine-tuned to life because, well, how could we not have? With an infinite Powerball tickets, you're going to win. Okay? And that's what he's saying. There is one small bit of evidence from the multiverse I want to share with you. We need to look at the CMB again. Remember that cosmic microwave background radiation? And there's a spot that we can see in the sky that's exceptionally cold, exceptionally devoid of matter. And galaxies, this huge void in the cosmos where there's just way less stuff than everything else. Okay? Again, that's what the picture looks like. And we're looking down here. You can't really see it because of how they've mapped this three-dimensional thing onto a two-dimensional map. But it's down here. And it's the coldest space in the universe with the least matter, no stars. It's just this weird big void. Okay, they call it the great cold spot.
That's just a projection.
It is, yeah.
They can center it any way they want.
Correct.
Why do they? If that's the point of interest, why not put that?
Well, and we blew it up here, so you can see. So they refocused it and everything. Yeah. Okay. So Again, we can kind of see it. It's
Yeah,
And the
if
question
they
is
make a
this-
map with the US right smack dab in
Right.
the middle,
Yeah.
you think they could.
yeah. They rearrange it. Well, we don't live in a cold spot, to be clear. So this is not where we live.
No.
We live kind of in the middle over here. So, the idea is that this is evidence of another bubble universe from the inflaton field bumping into ours. And it's like inflating and like spreading stuff apart. Like you see this, this void. And then they're saying, oh, this is definitely evidence. There's another universe crashing into ours right there.
If it was crashing into ours, wouldn't it generate heat and not cold?
We're not necessarily sure, but with the inflating universe, the idea is it would like spread stuff apart. So like you drop a rock and the waves go away from it, and you have this kind of calm space in the middle. Okay, that's the idea here. And it's possible that that is in fact evidence of the universe. What do you think that the odds that something like this could actually happen by chance? This cold spot. Again, many physicists look at this and they think it's absolute evidence because the odds are so vanishingly small that something like this could happen. It's definitely evidence to the multiverse. What do you think the odds are?
The odds are so vanishingly small for everything that we've seen in our observable
This
universe.
is definitely evidence to multiverse because there's a 1.85% chance it could happen.
Well, that's I don't believe that.
It's about 1 in 50, a little worse.
Oh.
So there's a chance of 1 in 50.
No.
And this is concluded as definitely evidence multiverse from crashing in. Do you think 1 in 50 chance would imply design? If we had fine tuning of the chance of 1 in 50, could we conclude design from that?
No, it's like
No.
flipping it.
It's not flipping a coin, but it's flipping a coin a couple of times, or getting like one number on the roulette table. It's possible. Okay, and so here's a discussion of that particular spot. Standard cosmology cannot explain such a giant cosmic hole, and made the remarkable hypothesis that the W map, that's the satellite, cold spot is the unmistakable imprint of another universe beyond the edge of our own. And if true, this provides the first empirical evidence for a parallel universe. Now, again, it's certainly possible. I don't find it particularly compelling.
This is just getting. That was evidence.
That's
that
the
was
best evidence for a multiverse.
That was good evidence.
That's the best one, okay?
That was
So the
best
question
evidence.
is, when we compare these possibilities, what can we conclude? It's not eternal. It needs to be multiverse, but we have no evidence for it. Inflation is largely just made up. I mean, pretty much all those things are just not compelling to me. I am not convinced by any of these in the slightest. In fact, but I do see compelling evidence for the alternative hypothesis. And in fact, we do see the design, we do see balance, we see purpose, we see incredibly low probability. All these things, all those boxes get checked. Again, here's that quote from Fred Hoyle again. And this is the guy that came up with a steady state theory to essentially explain away the Big Bang. And even he admits this, after his theory was largely disproved. It says, a common sense interpretation of the facts suggests a super intellect is monkeying with physics, as well as chemistry and biology, and there are no blind forces worth speaking about in nature. So this guy actually thinks that aliens created us.
What?
He thinks aliens created us, so he's talking about aliens in that.
No,
Yeah,
or the aliens.
that's the good question.
It's turtles all the way down.
It does. It's turtles all the way down, unless they're eternal. In which case, why don't we just call them God? Okay. So that's it for today. Again, I hope that this sort of wrapped up what we talked about last week, where you can kind of understand that our universe is specifically seems purposely built just so we could be here, which is cool. And we're going to dive in next week and the weeks following into just how much design we actually see in our own lives and the life that we see here. So, Lord be with us as we go. Amen.